Hello, I'm going to solve an example of an exponential growth example from the book. I slightly modified the example by changing one of the numbers. You can see there 8 on top of that pink patch is changed by me, and also I added a few parts to the question. So, to the work. There's a locust plague, and we know what is the area of land eaten given by the function a after a number n of weeks. So let's write here the function a of n is given by 8,000 times 2 to the power of 0.5 times n. So I'm going to show how we can solve this question without using a calculator until we get to part F, where it says use your calculator. So up to there, we are not going to need it. For the first part of the question, we are asked to find the size of the area initially eaten. So that will be, if it's the initial, then that means that n is equal to 0. So we are talking about 0 weeks, so the moment of the initial observation of the plague. So when n is equal to 0, then we can find what the area eaten is. We have the 8,000 multiplying, and then we're going to have 2 to the power of 0 because we are multiplying 0.5 times 0. So actually we just have 8,000 multiplied by 1, so 8,000. So 8,000 hectares is the initial area for part A. In part B, we want to find the area eaten after 4 weeks. So A of 4, so we're going to have 8,000 times 2 to the power of 0.5, so half times 4. So we are saying here 8,000 times 2 to the power of 2, which we know is 4. So this is just 32,000, and you see we had no need for a calculator. For the second part of part B, we want to know the same, but now for 8 weeks. And here's where I change the number because the number before was 7 and then we'll need a calculator. But for 8, we don't need it because we're getting 8,000 times 2 to the power of 1, and then we have a half multiplying 8. So here we are doing 8,000 times 2 to the power of 4, which is 16. So we are doing 8,000 times 16, and then, okay, let's see here, 16 times 8, can do that. 48 for extra, so it's 128,000. Forgot the units here, so we have answer part A and B. And now we want to use the information we have from part A and B to sketch the graph of the function A against n. And we are going to do it just knowing the 3 points that we know. We know that the function at 0 takes a value 8,000, at 4 takes a value 32,000, and at 8 takes a value 128,000. We also know how this function looks like because this is an exponential function. Let me just clarify something here. We say that exponential functions were functions of the form a to the power of x. Here we have a slight modification of this because we also have a number multiplying an 8,000. So we can say that we have k multiplying a to the power of x. So a function like this, we also know how it looks like from knowing how it looks like a function a to the power of x, because we are just multiplying by a constant, so just a positive constant. So we still know a lot about that function. I'm cheating a little bit here because here we don't have 2 to the power of x. We have 2 to the power of a half times n. But this is the same as saying 2 to the power of a half and then all of that times n. So this is, well, we can write it as square root of 2, all of it to the power of n. So now I will write my function a as a number, positive 1 in this case, multiplying the base square root of 2, which is greater than 1, and then to the power of n. So this function is going to look like one of the functions of exponential growth like this. So we are also using that information when we try to sketch the graph. I wrote over here the definition of the function and also the points that we found before. And now we have to go ahead and find a good scale for each axis so we can sketch the function. So, how do we do this? Well, let me draw the axis over here. We are only carrying out what's happening in the first quadrant. That is because, well, we know that the function itself is going to only take positive values, and n is also going to be greater or equal than 0. So on this axis here, I'm going to have n, it's the time in weeks, and here I'm going to have the area in hectares. And I have to pick a scale so that it makes sense to have 8,000, 32,000, and 128,000 represented in the y-axis, and I want to be able to represent 0 weeks, 4 weeks, and 8 weeks, at least in the x-axis. So in the y-axis, let me count how many squares I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I had 13, that will be very nice because then I'll be able to just say that each square is 10,000 hectares. So let me move this a little bit up. Yeah, so I'm just gonna extend the axis 1 square more so it fits better the scale I want to use. So here is going to be 130,000 hectares, and then this is 10,000. And I'm going to be able to fit all the values I care about. In the x-axis, let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, that sounds good, up to 10. We don't need to go much further than that, so just stop there. The information I have for sketching the graph is only about weeks up to 8, so I won't try to extrapolate information about weeks that are much farther. Now when we are ready to add the points, we know that when n is equal to 0, the value is equal to 8,000. So, okay, let's use a different color here. This is over here at 8,000 in the y-axis, the first point we know. Then we know that when n is equal to 4, so 1, 2, 3, 4, we are here. Then we're going to have 32,000 in the y-axis, so let's say it's over here, 32,000. Of course, we are approximating, we are not being super precise, but we'll try to do a nice picture so we can get information that is more or less accurate, and then we're going to check if that information was actually accurate. And then for 8 weeks, that's over here. We know it's 128,000, so that will be over here, 28,000. So, okay, I need to go a bit farther this time, and I need to go up the line x equals 8 to find my point. Okay, it's here. Split out. Okay, so I have these 3 points, and I also have a knowledge of how the function looks like. I'm not gonna try to do something like, okay, let's say I go from this point to the other one and then I go down and up. No, we know the function is not doing that. We know the function is increasing and we know the shape, so nothing weird is happening over there. So let's see if we can draw it. I'm not super happy about how that looks. Let's try again. Okay, I think that looks okay. So y equals a of n is my function over here. Now let's see what we were asked to find for the parts D, E, and F. Actually, let me copy them here. For part D, we want to use a sketch to estimate the area eaten after 5 weeks. So we are going to locate in our x-axis where 5 weeks are. They are here. And we're going to see what is the point of the function that corresponds to this 5 weeks. Is this point over here. So this is the point that has coordinates 5, the area after 5 weeks. And we can get an estimate of what that area is by finding the y-coordinate of the point. That will, I would say, is around 45,000 according to my sketch over here. So let's write over here 45,000 hectares. For part E, we want to estimate when the area eaten will be 70,000 hectares. So I need to locate 70,000 in the y-axis. 50, 60, 70,000 is here. And we want to see what is the point of the function that has that y-coordinate. Is this point over here. So this point is going to have some number of weeks and then 70,000 as the y-coordinate. So let's go down to the x-axis to find the number of weeks. Over here it looks like it's going to be approximately 6.5. So right here 6.5. The question doesn't say anything they want us to say in exact weeks or what, so I'm just going to approximate to 6.5, the x-coordinate of this point over here. Now, for the last part, we want to check in our calculator how good the estimates are. For part D is fairly easy. We are just going to go to the calculator and find what is the image of the function a when n is 5. So we need to find what is 8,000 times 2 to the power of 5 over 2. So let's do this in the calculator. 8,000 times 2 to the power of 5 divided by 2. Well, there we go. It says 45,254.8. So this is 45,254.8. That's the 6. That's the approximation the calculator gave me. That's, would say, to three significant figures. This is 45,000. Oh, sorry, 45,200 hectares. So I'll say that our estimate of 45,000 was very good. I'll write here, good estimate. Now we want to see what is the number we need to apply to the function to get a result of 70,000 hectares. Also, we're going to start with what the picture is suggesting to us is that the number is 6.5. So let's try with 6.5 and see how far off we are. Sorry, there's a mistake. 8,000 times 2 to the power of 6.5 divided by 2. And this is saying that is 76,000. So let's look back at the picture of the function, the graph that we sketched. So a of 6.5 was approximately 76,100. So this is a bit more than what we want. So that means, because the function is increasing, that we should try to see what is a for a value that is a bit less than 6.5. So let's try with 6. Let's try to see what is a at 6. 8,000 times 2 to the power of, well, 6 divided by 2, so 2 to the power of 3, which means 64,000. So that's not enough. So the number has to be something in between 6 and 6.5. So let's try 8,000 times 2 to the power of 6.3 divided by 2. That's still a bit too much. So let me copy this and try instead 6.1. That's a bit too little. So 6.2. I think we are very close with that. Our approximation was good, but it will be better 6 points.